Lunch and Learn. My name is Kevin Holbrook. I've spent the past 15 plus years working at CADimensions, doing Lunch and Learns and other training sessions. Today's Lunch and Learn is called Mechanize It, and more than a few times over the past several years I've been asked about mechanical mates in SOLIDWORKS and maybe to give some insight into the do's and don'ts of each and limitations and why and when to use them. So that's what we're doing today. So we're calling it Mechanize It, but we're going to cover the mechanical mates in SOLIDWORKS, and I threw a few other things in there just to make sure we have a good cross-section of what we're dealing with today. So our agenda is this. We've got 7 mechanical mates that are included in the mate section of SOLIDWORKS. I'm going to go through each of them, cover the ins and outs, and one by one. So let's go ahead and get started. First mechanical mate that we are going to talk about is the cam mate. There are, in most of these mechanical mates, they gain you some leverage as far as the ease of applying them. What I mean by that is, in a lot of cases, they actually lock down more than a standard mate. However, in a lot of cases, there's also particular entities and a particular way that you have to build something in order to utilize it. And the cam mate is no different. So in order to use a cam mate, there's really 3 things that are requirements for the cam mate. The first one is the faces that we select that form the cam itself. It needs to be closed and continuous. I'll show an example here where I try to make a discontinued cam and the software screams at me here. The cam should be extruded from a single profile. So it's not just good enough to create it as a closed form. I've got to do it with a single profile to create the outer surfaces. Then the third requirement is all of those faces must be tangential to each other. Now, on bottom of all of these slides introducing each of these mates, I also have a little note in there just going over what selections are possible. My assumption is that if you were to grab up this video, you can look at this and see what your selections should be. So let's start with a couple of examples of a cam mate here. Okay, so here we are in SOLIDWORKS, and I want to get another thing right out of the way that I'll be using quite a bit in just presenting these, and that's the ability to hide and show components. And for some reason, this was added in the last few releases, and not a lot of people were aware of the functionality. So if you see parts disappearing, I'll explain to you now how that happens. If you hit your tab key now in 2015 and 2016, that will make a component disappear. Okay, so all they have to do is be moused over it, hit tab, and it will disappear. If I want it back, I hold shift tab, and then I just drag my mouse over the top of where that component used to be. That component will now come back. Now I'm going to hide those components once again. There is another option to that, which is control shift and tab. That will show you all hidden components and allow you to select the ones that you want to show. So for all the mate presentations today, I'm going to be using a lot of the ability to tab in order to get what I want showing available to me. So here's a perfect example, a rocker cam profile here, and I need this thing to follow this cam path. If we look at how the cam path was built here, let me open this part, take a look at the feature that created this cut extrude is a single profile. Okay, that single profile, if I edit the sketch, is made up of a spline. So a spline in this case is going to at least be tangential all the way around the curvature of the spline. Therefore, we've met 2 of the requirements, which is single feature profile it's closed, okay, and we need to have tangential surfaces. So let's go ahead and just take a look at what we can do here. Okay, so in order to get to your mechanical mates, we must go into the mate tool. Currently, if you're using any of the mate shortcuts by just selecting surfaces, the mechanical mates do not utilize those tools. For those of you who are trying to understand what I'm saying here, if you select two surfaces by holding down Control and let go of Control, the pop-up that gives you the shortcuts to the mates, you will not see mechanical mates listed here. So I must go into the paperclip, the shortcut to do that. Another little tip here, if I hit my S key in the keyboard, that's what you're seeing for the pop-up, so I don't have to go to the command manager to get access. Okay, within the mate dialog, there are three sections: standard mates, which we're all, I'm sure, used to, coincident, parallel, perpendicular, concentric, those types of mates. We're going to focus specifically on the mechanical mates, which are the 7 that we discussed earlier. Starting with the cam mate here, you'll notice as soon as you select it, just like all other mates, it changes the selection dialog at the top. I need to select two things: the cam path, which can be the surface that I want. Now you'll notice here that it's telling me that there is a slight little issue with this outside surface. As I go to try to select it, it says the face must connect from other faces and must be tangent. So in this particular case, I am able to use the inside surface because that is one closed loop, where the outside surface has this little jump to it here, okay? The follower is the cylindrical object that's going to be following the cam path, and this can be a face of that object. Okay, there are no other parameters to define in this. It's the face and the path. Essentially what you're getting out of this is a tangential mate. It's going to maintain the tangency to the surfaces. And in the end, you are able to, in this case, follow this thing around the entire path. And I'm not sure how well this is going to come through on the video of the webinar. If I want to bring in some of these other components, I hold Control, Shift, maybe grab some other components in here that I want back. Okay. And you can see that what the motion is that I was trying to achieve with this. Okay, so there's one example of the cam mate. Let me get rid of this and take a look at another one here. Very similar in nature. This little rocker here will be controlled by the cam. Same process of getting access to it. There's really not a whole lot as far as selections with the cam mate. In this particular case, our path can be any of these exterior surfaces. Notice it automatically selects all the surfaces in a single selection. The software is going to recognize that, and in this case, I select the follower, which you'll see that it moves it tangent to that surface. And for this particular mate, I can now rotate the cam and have it move. Okay, so there's the cam mate. Continuing on, the slot mate. Slot mate is fairly new. It started really when we were able to get slot sketches available to us. A slot sketch is that sketch entity that allow us to create angled or straight slots in a sketch environment. And then more recently, we got slots added to the Hole Wizard. Great thing is it supports both the Hole Wizard slots and slot sketches. Now I wrote in here other tools because as I was digging into the limitations of this particular tool, all of the help and documentation basically says you got to use a slot sketch or a Hole Wizard in order to get the slot mate. However, that seems to be not the case. It might be an undocumented feature. If I were to just sketch line, arc, and put tangencies, the slot mate does work in this case. So just keep that in mind. When we do put or mate slots together, we can do a slot to slot. I'll show you some of the options available in the slot here in just a moment. And as always at the bottom, to use this mate, I give you some idea of the selections available to you. So let's take a look at an example of a slot mate here. So this is just a straight slot in this particular part here. If I wanted to, let me just suppress the one here, wanted to add that mate, I would just go right to my mechanical mates. One thing I wish they did have is the ability to go right to the mechanical mate section. As of right now, you cannot do so. So that's a little bit, I don't think you're adding too many of these at a time, so maybe not an issue. The slot mate has multiple options for constraints. The first thing we got to do is select the entities to mate. Now this is very much like the cam mate, that if I select a surface that belongs to a slot, the software is going to take a look and understand that if it meets the requirements for a slot. Now I mentioned you can sketch it, you can use a slot sketch entity, and you can use the whole wizard slot. Now there are certain sketch slots that maybe have weird angles or bends to them where it just isn't going to recognize it to be a slot in this case. Now, for constraints, we have a free constraint which says the entity that I select next is free to roam within the slot. Now the entity I'm talking about is just this little pin on that wheel here. If I select the pin, that's what it's going to use to define the other constraints. However, I do have options in here to center that pin in the slot. You might use that for a fastener that's going to be in a slot, but you want it centered within the slot, or some piece of hardware that goes through a slot. We can also define the distance along the slot. The great thing about that, if I select that, what it does use, it uses the center point of one of the end axes of the slot to give you that distance, and you can define what that is in the units of the document that you're working in. Okay, percentage along slot basically says, okay, I know from center to center on the end is 12 inches. If I want to be 10% along, I'm 1.2 inches. So it's just some simple math that the software is able to do. In this case, I do want a free slot mate, and you'll see in this case with all the other mates what happens. The control is really just sliding that pin along the center axis of that. It doesn't necessarily mean that there is contact. There does not have to be contact here between the surfaces. It uses the axis of that pin that's in the center. So it's not solving for any kind of tangency in this case. It's using the axes. Now, let me open up this part and just show you a few things here. So this part, this example, I actually had to put the cut into the part itself, and I did that using a slot sketch. What's nice about when you use a slot sketch or the whole wizard, the result is some axes not only at both ends of the slot, but also at the center of the slot. So this is what facilitates the ability to lock the center or to control distances from essentially the center points of both ends. So that's why all of these things are going to work very, very well. Just show you one more example. I'm going to try to do this for each. Let's see, here's just another example of that. If I move this along, again, the slot it's free in the slot and can move it back and forth. Okay, so there's our slot mechanical mate. Next one is a hinge mate. Now this one, not very hard to use, but it does quite a bit for you. The result of this can be utilized in motion to help keep from having redundant mates. You can use it for animations. I mean, there's a lot of reasons why a hinge mate helps. Essentially, a hinge mate combines both concentric and coincident mates in one single command. Okay. It can, however, fully define a part. Okay. I made a little note in here, beware of limit mates. I'll talk more about that. I'll flip back. This gives you the ability to create one mate instead of 3 mates to lock it down. Now the reason I have that little chart here is because of concentric mates. So I told you that this combines both concentric and coincident, and as far as the selections for concentric, it's exactly the same as any other concentric mate. This is the chart out of the help, which tells me the things that I can select to create a concentric mate. When it comes to the coincident portion of the hinge mate, planes, planar faces, edge, or point are available. Okay, now let's talk about how limit mates comes into this. Let me give you one example here, and then we'll talk about the limit mate side of things. So, very simple, hinge mate, go to mates, mechanical, select your hinge. You'll notice at the top of the dialog we have selections for our concentric pieces. Now this is where I had that chart. There's many, many different things that you can select to make two things concentric. I'm going to keep this simple here. I'm going to say I want this cylindrical surface and this cylindrical surface concentric. For our coincident, this can be edges or faces. I can just, in this case, I'm going to select this face and this bottom face, and it's going to slide everything together. 2 mates in one single command. However, as you noted on my slide, I said 1 mate instead of 3 mates. So how does that come into play? Well, let's take a look at another example. Okay, here's an example where we have a knife that we need to rotate some distance. Okay, using a hinge mate, clear some of these here. Okay, what I can do is I can say, you know what, I need this to be my concentric. I need these inner surfaces, let's say here and here, to be my coincident. And then I have an option at the bottom to specify the angle limits. So in this case, I want to specify the angle limits, and I got to give it 2 surfaces to define the angle that it can move relative to each other, just like a hinge can move certain angles. So in this particular case, what I'm going to use is this surface on this cutout and this surface on this cutout. Now you'll notice it gives me the exact same options that I have in a limit mate. It says, okay, what's the initial angle? Okay, notice as I adjust this, I get changes to the initial angle. Okay, let's find an angle maybe where it's not touching here. Okay, this is going to be some angle. Then we can say the maximum value and the minimum value. Now, I'm just going to leave it like this just so you understand what we're dealing with. I can also change the angle direction, flip it, and the result of this, I need my coincident face on this side. Okay, the result of this, and I know this is going the wrong way, is a rotation, a hinge mate that only goes the limit as well as the concentric and the coincident all in one shot. So this is 3 mates in one. Anytime you have coincident and concentric together, you know, what's the most famous one of those? To me, it's a fastener in a hole. What if I just add a hinge mate and it puts both the coincident of the bolt as well as the concentric of the shaft of the bolt, all in one shot. Okay. Continuing on, we have gear mates. Gear mates in mechanical uses ratios of rotation. We have to define the axis of rotation, either manually defining the ratios, meaning I type in the values, or I automatically define the ratios by selecting cylindrical surfaces. Now, even if I select cylindrical surfaces, I can override the value, kind of like we can in the hole wizard. If I override the value, it turns up yellow. Now, note here is that it does not prevent interference at all. So it's not like it's dealing with the gear teeth meshing and the exact motion and movement. We're just putting in a gear ratio to show what it could or should look like. A little note at the bottom, and this isn't necessarily always used for gears. Anytime you have components that rotate together at some ratio, whether they're touching or not, you can use a gear mate to do that. So let's take a look at gear mates. So here's an example, and what I'll do here is just unsuppress a few of the gear mates that I have, just so you can see how this thing is going to work. Got one more here. What this is going to do now is what looks like driving the gear teeth one onto the other, when in reality all it is 4 separate gear mates that are working all together. Now let's start the very first one. I'm just going to edit the mate here. First thing is your mate selections. Now these can be edges or faces, surfaces of the model. Let me show you how to add one here, and that'll helpful on how we got there. If I go to the mechanical side of things here and go to gear, my selections can either be an axis or a surface. If I select an axis, I've got to define the ratio between the gears myself. But watch this. If I just select 2 gears, okay, I'm going to select the inside of the teeth here. So there's my first gear, and I'm just going to select the second gear, which is over here. You'll notice that the software automatically pulls off the diameter of those surfaces that you selected. So in this particular case, you can see that they're both the same diameter. What we do from here is that dictates the ratio of movement between them. Now you can see 75 to 75. I do have the option to reverse the direction of these, but if I wanted to override the ratio, let's say I wanted the ratio to be 75 to 1,000 for some reason. As soon as you adjust the parameter, the ratio parameter, it goes yellow, first of all, to let you know that you've overridden that parameter so that you can make an adjustment to it if you need to. So let's look back at the gear mates that we have already defined. So in this particular case, they use 2 edges of the gear and defined the ratio, overrode the ratio because they are the same inner diameter that was selected. You can see that we're now changed the ratio to from 40 to 20 because of the difference in the gear sizes. Now you'll notice in here that there's not a place to put another gear in here. So right now I'm driving one gear to one other gear. So in order to get something like a drivetrain together where there's multiple gears that will be working, I actually have to have multiple gear mates. So here's the second gear mate, which is the same 40 to 20 ratio, and you can kind of make this out. When I select the gear mate, this blue text here is the value 40 to 20 that we have, and then we have just the same ratio but 20 to 40 going up to the others, and that's what gives me the movement in the ratio. Now the only other thing that I would recommend before using this is before you put the mates on, just move your gear so the teeth are not touching each other or they're just touching. That way when you apply this mate, the teeth aren't interfering with each other, because as I stated, this will not affect the interference of the parts. Okay? So there's your gear mate. Continuing on. A rack and pinion mate. So rack and pinion allows us to take a translational movement and tie it to a rotational movement. We can define that using a pitch diameter and then a rack travel per revolution. So as something rotates a certain revolution, what's the travel of the rack itself? So there are a bunch of different selection options that you can see on the bottom of this slide. Those are also in the help. I wanted to give you a few examples of this. All right, here's our corkscrew. Do the same thing here. Take a look at the mate. If I go into the mechanical mates, it's just another option in there. And you'll notice that it has something very similar to a mechanical mate in that when we override a value, it turns a certain color. But where does it get this, in this case, pitch diameter for the pinion? Now, first of all, at the top, we have to select something to represent the rack, and we have to select something to represent the pinion. Okay? The rack in this case is just the corkscrew. We want the corkscrew to move along its axis down some distance. And then the pinion is the rotational movement. In this case, by selecting the inner edge or inner surface, it gives you that diameter. So it creates essentially a ratio. Okay, so as I rotate this thing, it's going to slide this down a certain distance. Now we can change this and say I want to define the rack travel by the number of revolutions. So as this thing goes through its full motion, what's the full distance of travel? Okay? The result of this is a motion that looks like this. Okay, the rack is the corkscrew that's going up and down. The rotational movement is the other. Very, very simple to apply, but done in a single mate. Let's look at another example here. This one combines a few of the elements that we've been working on. Let's go ahead and define it in this case. Let's just make sure I didn't leave one on here. Nope. All right, so we'll go to our mechanical mates. We'll grab our rack and pinion. I need to first define my rack. Now the rack can be a surface, it can be an edge. I'm going to just use the edge because it's going to use the length of that edge to dictate the distance or movement that I have here. Now I'm going to use in this case rack travel per revolution, but I have to define the pinion also in this case. So we're just going to use some surface. I'll use the inside surface here, and then I pick what is that travel per revolution. Now I happen to have worked this out a little bit to know where I wanted this to be, and the result, okay, is a nice movement. Now the rest of this movement is just done using gear mates between the gears, and this is just connected to this through a pin. So this whole motion can be illustrated here, just a few mates. So we can start to make things look the way they should. All right. Screw mates. This one's very, very simple. It's showing how something might screw in, rotate, and translate all in one shot. We can define it by revolutions per inch or millimeter. The units come from the document that you have open, or the distance per revolution. This also does not prevent interference. We select face, edges, or axes for both components. So this one is pretty simple to utilize. Let's take a look at just this example here. So threads are not modeled in this case. It's just some simple floor jack. If I go ahead and select my mechanical mate for a screw mate here, revolutions per unit. Now this happens to be in millimeters, or distance per revolution. Now make my selections. I'm going to go ahead and select this cylindrical surface here. And then for the other component, I have to select, again, another cylindrical surface, doesn't matter which one. And then the distance of them moving relative to each other using the axes based upon the number of revolutions. So instead of 1 millimeter, let's do, I don't know, 25. So as this thing works its way around, try to turn it through here, you can see that it will move up and down based upon the units. Hopefully that's coming across pretty good here. Okay, let's show another example of that. Just another simple example. Obviously a screw or fastener in a hole. If we take a look at this one, I've already defined it here. So this is distance per revolution. For every revolution, we're moving a 1/4 inch, and what you end up with is the fastener that as you rotate it in, it rotates a 1/4 inch into the surface. Okay, so easy to define, very simple. You can put a motor to those in motion so that you can see that in action, maybe save a video out or so on and so forth. So very simple mechanical mate, but it does give you some extended capability. Universal joint mate. Another one that's very simple. What it's trying to do is just link two parts, link the rotation of two parts. In a lot of cases, you already have the linkage between the two parts defined, but it doesn't necessarily have to be with these. You just need to select some circular entity on both components, because what it's using is the axis and the rotation of the axis to define the rotation. So any kind of off-centered rotation as well. Let's take a look at this. Okay, universal joint here. Very simple to define. Okay, if I wanted a universal joint, go to my mechanical mates, universal joint, no other parameters down here to make any selections at the top. It's just defining the entity is going to mate. Whatever you select, it's picking essentially the axis. So it doesn't matter if they're two different cylindrical surfaces. It's going to use the axis to define them. Now there's only one other option within the universal joint, and this is a joint point. This is where you define the point of connection between the two. In this case, it's not valid. It's the intersection of the two axes, but they don't necessarily have to be mechanically a universal joint. You can simulate, you know, two things rotating, transferring energy around two separate axes, but you define the point in which the axis exists. Okay. The result of this is very simple, that whatever you rotate one is going to rotate the other. Very similar, and I could have done this with a gear mate and just made the rotations 1-to-1 and gotten the same result. So that's our universal mate. Okay, now I had two little addendums before we close today. I wanted to give you an idea of all the mechanical mates, but I often get asked, well, what about belts? Belts are kind of a mechanical thing. There's no belt mates. Well, let's take a look at what SOLIDWORKS does with belts. All of these things are kind of in a different spot. Not really sure why. They're using different functionality, but I want you to be aware that they do exist. in the assembly mode, you have the ability to get to assembly features, and in there is a command called belt or chain. Okay, if I select belt or chain, I can now do exactly what we did before, and that's start to select objects that we're going to wrap the belt or the chain around. Okay, now I can control the direction in which we do that. Am I engaging it one side or the other? So on and so forth. It calculates the length of the belt. You can see that down here, 2,058 millimeters. And it can actually create a part for the belt. The reality of this is what it's just done by engaging the belt is created something that represents the ratios of all the pulleys, very much like a gear mate. But if you're looking to do that type of thing, it's kind of in a different spot, right? We have a regular mates folder, and then we have this feature for a belt, which is a little bit unique. So I often get asked when going through mechanical mates, what about belts? Okay. One more example. What about chains or linkages? Well, I could have simulated a chain using the belt or pulley function, but what if I physically wanted a chain to show up? Well, this is a new function in SOLIDWORKS that was added very recently. Let me show you where this one is found. Now, this one is found in a different spot in the assembly level. There's a pattern called a chain pattern. Now, if I added this feature, we could probably do an entire lunch and learn on chain patterns. Very simply, there's a path, and we define the linkages that are following that path. In this case, it's a chain with an inner link and an outer link. Okay? You tell it the faces on which these links connect. You can see here, inner and outer faces. It's really automatically creating coincident and concentric mates between them, so these chains can rotate freely. And then you align them to this sketch that's used. Now, the option is to make it dynamic, which means this thing could work. And how this will come across in the webinar, but hopefully you can see a little bit of this. It's not a mate. In my head, it kind of is because it's adding mates somewhere along the way, but found in a completely different spot. So there's your chains and linkages. Now, I want to thank you for attending today. Couple kind of odds and ends. Don't forget to ask us if you're doing any kind of PCB work. SOLIDWORKS PCB was released on July 1st, and we can talk and show about it now. So all your board design and getting that board design in SOLIDWORKS and making mechanical changes. Also, we've been doing hands-on test drives for a lot of the other products now. So if you're interested in hands-on test drives in MBD, Visualize, Composer, PDM, even SOLIDWORKS Premium, we can do that as well. So I want to thank you for attending today's Lunch and Learn. If you have any questions, please post them in the questions section. Otherwise, we'll see you at the next Lunch and Learn. Take care.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.